Okay, thank you for the introduction. So I would like to talk about our work concerning interaction of motion and stereoscopic 3D. So first two topics will be mostly about display technologies, and other two topics will be more about application, about content production. So out of possible multiplexing technologies used to deliver left and right eye content, I would like to concentrate more on color multiplexing and time-sequential displays. So a simple example of color multiplexing display are Anaglyph glasses. They are very popular because they are cheap and also very universally you can print Anaglyph content to the paper, but they have rather poor colors, and there is additional problem of asymmetric eye filter transparency. So if you look in this table, the transparency of filter on each eye differs with the type of the Anaglyph glasses, and it can be quite significant. And this leads to the Pulfrich effect, which is very well known since 1922, described by Karol Pulfrich. And it basically works as follows. You have an object, some moving object like this flying bird, the blue one, at some position and depth, but the other one, other eye, the eye with red filter, gets attenuated signals, and that takes brain longer to process. So there is additional disparity caused by that, and the consequence is that if you have a moving object behind some static fence, for example, then you will have a depth conflict because the object can be moved in front of the obstacle. So we have used three simple examples of Anaglyph glasses, and we have run a user study where user can adjust time delay of one eye with respect to the other one in order to stabilize the moving pattern in depth relative to the background. We also tried varying speeds of the stimuli. We tried different luminance levels, but we didn't get effects in that. Instead, we got statistically significant difference between glasses, which corresponds to the prediction of the Pulfrich effect model, depending on the brightness ratio of two eye signals. And from that, we conclude that if presenting 3D content on Anaglyph display, you should always delay the signal of the darker eye image by corresponding value, and that you can either use from measurements done a priori, like those we did, or you can use our applet that is available on the internet to measure your own glasses. The advantage of this approach is that it's independent on the display because, as I said, it doesn't depend on the brightness, for example. Other type of displays used in stereo 3D are time-sequential displays, like NVIDIA shutter glasses. And they have one problem, which was nicely described by Hoffman in his paper. You need to decide about how to render, how to capture the content. So either you capture both images at the same time, pretending they happened at one exact moment of time, or you capture them by alternating a protocol that simulates the delay that will be produced by presentation. But we also noticed that it depends on the way how you perceive, how you look at those images. So if your eyes are static, look at one point on the image, then you should render images with a simultaneous capture protocol, because then both images will be projected on correct corresponding places of retina, which is not moving. While if you are following the moving object, then you assume that in the next moment of time, the object will be moved to another location, so you need to display it at the proper location. So in other way, you need to capture in proper time. If you use other two possible combinations, you will again get some additional disparity, which is false and should not be existing in the content. The magnitude of the effect grows if you start to repeat frames, because you cannot render so fast, or you have a triple flash protocol in the cinema. So what we propose to do is to take a signal of one eye, take two consequent frames, and analyze those two frames in order to decide between those two protocols. So we basically try to estimate if a user will be trying to, it will be pursuing a motion in the image, and we do it locally. So we use a saliency map in order to estimate how likely is it that he will try to follow some object, and also texture periodicity map that tells us if it's easy or hard to track some object. If we combine this, we use it to interpolate between, locally interpolate between simultaneous and alternating capture protocol. We simulate the other one by warping so that we don't have to render twice. And we combine them using blending. So that that way we get a new frame displayed for the given eye. This video cannot simulate the effect because for that I need a high refresh rate display. We use magenta green glasses to simulate the alternating protocol, but it shows that there is no artifact in the middle image that is from our method compared to the top one as simultaneous capture and bottom one as alternating capture. They don't again, this video doesn't capture the effect because of a slow refresh rate of this video. Another way, another important part of stereo 3D content production is maintaining the user viewing comfort. So for that, we often want to move the content inside so-called comfort zone. And there are several methods that allow us to do that. So simple one is to alternate, to modify the camera parameters. So that was described in this OSCAM paper. Other way is to use some tone map, something like tone mapping, but over disparity image in order to non-linearly modify the disparity in post-processing. Or you can also do this in a perceptually linearized space that also takes into account invisibility of disparity without luminance support, so that you can compress more. But it has some problems when motion is introduced. So imagine the scene on the left, view as on the left, where there is some depth that is not visible, like the valley in between those two hills. Then if we do compression, we will basically remove the valley because it's not useful to spend depth budget on it. But imagine that the balloon is moving through the valley, and then he gets to the zone where the disparity doesn't change. So the motion represented as change of disparity over time will be altered by this. So what we want to do is to to maintain the manipulation done by the other method, because that was done to get into the comfort zone, but we want to locally restore the motion. How we do it, we take the original disparity and the manipulated disparity given by some arbitrary method, and then we subsample in space and time in order to cover a larger part of the trajectory, and then we can minimize the distortion of motion, upsample back, and apply the new disparity that we obtained to an image that we present to the user. So again, we have the original disparity, some black box of manipulated disparity that goes both into our optimization framework, and the output is a new disparity. In order to find the new disparity, we have energy equation with 4 terms. So the first one just tells that the disparity should be similar to the manipulated one in order to keep the comfort zone. The second one tells that our optimization should be spatially smooth with respect to the modified disparity, so it shouldn't be very different at each pixel. Then we have a similar one for a temporal domain. And the fourth one is most important because that connects the disparity with the original disparity and tries to restore the motion. So we cannot restore the speed because the space was deformed and the distances were changed. But instead we try to restore the acceleration, so second order change of disparity, in order to keep the trajectory similar to the original one. So if there was ballistic trajectory, it will stay as ballistic. We do this in a perceptualized space. We use Weber-Pechner law to say that small changes of small magnitudes are more perceivable than small changes of large magnitudes. So something that is very close to the diagonal here is not perceivable, and we don't need to optimize for it. So again, we have 4 equations which we can write down in a math form as some difference of 2 quantities measured by L2 norm. Then here we use the perceptualization for the temporal change. And then we can minimize the sum of this energy. We use simple gradient descent, except we add boundary constraints in order to stay in the input depth range. So we have run a user preference study. We ask for more realistic motion representation with reference. So we showed always the original video, and then we showed we showed the manipulated video and video that we optimized after the manipulation. And yes, we achieved a statistically significant preference of our method over the manipulation. So here I show this is the original stereo content without any manipulation. This is the stereo content manipulated by some operator. And this is the same content optimized to restore the original motion. You can play again. Okay. So again, this is the original stereo content. This is manipulated with distortion of motion. And this is restored by our optimization. We also had a theory that manipulating the disparity will cause user performance to go down in some tasks that require depth estimation, especially connected with motion of object in depth. So here we had a task where users had to estimate a trajectory of a ball moving in 3D space, and they had to estimate where the ball would land if he saw the entire trajectory. We tried linear trajectory and ballistic trajectories. And indeed, we found that distorting the disparity makes the performance go down. As you can see in the video, there are very few additional depth cues, monocular depth cues. So we try to stress the disparity depth cue. And that's for the optimization. And as I skipped one part in this method, I said that we produce the disparity, but we also need to apply the disparity somehow to the image content. So we cannot just modify the camera parameters because we do local manipulation of disparity, so we cannot have local cameras this way. So instead, we can use single camera. And then we don't get any 3D effect, but we can do depth image-based rendering, which basically warps the image and gives us 2 views, but that also has its own problems. So in simple case, when there is no background separated object, it works nicely. But if you have occlusions, then moving one object differently than the other one due to motion parallax introduces these occlusions, and these have to be treated. So if it's done improperly by some simple inpainting, then you will see artifacts immediately depending on the background. But we are from a computer graphic community, so if specifically dealing with computer graphic content, we can instead use another approach, and instead of moving pixels after the rendering where the information is lost, we basically warp the 3D mesh so that when rendered from center camera, it looks like it would be rendered from appropriate stereo camera. And because we can warp each vertex individually, we can achieve local disparity this way. And these occlusions are handled automatically. The nice property is also the fact that this can be easily plugged into any rendering pipeline because it is just additional step before the rendering, and the rest can stay the same. Of course, it requires rendering twice for 2 views. There is a comparison. So as you can see, these occlusion artifacts are gone. And one more in detail. So I've presented a few examples of interaction of motion and stereo 3D. Two examples were concerning displays, 2 were more into the application area. So I thank you for your attention, and I welcome any questions.
Okay.